Oh, start again. Now you're being recorded.
No, for everybody that doesn't, or for the few that don't know me, maybe a lot on this call. Todd Price at Western Automation. Been with Western Automation for a little over 30 years, and I get to hang out with Chad, who's on there, and Pierce and Chris and all that whole crew, and known Dan and them for quite some time. But anyway, our discussion today, what Pearson wanted me to talk about was some advanced sensing methods, in particular. And first, I'll have to apologize for my nasalness. I'm still recovering from being sick. But anyway, discussion today is going to be radar technology versus ultrasonic technology. And even though it looks like it's one or the other in terms of from a competitive standpoint, typically the two technologies kind of go hand in hand, and most manufacturers or suppliers of radar also supply ultrasonics because it's pretty much an application specific type product when you really drill down and look at what a customer is trying to do in some specific applications. Okay, first of all, we'll talk about doing some comparisons between the technologies. And if I can get my screen to open up and show me. All right, so can everyone see that? So ultrasonic level, typically level meters, level transmitters versus radar transmitters. Typically, when you're looking at the two technologies, it's basically two different measurement principles. Radar is basically based off of dielectric constants of material that you're actually looking at. Not too different from a capacitive type sensor. The only difference is obviously we're talking about radio waves, we're talking longer distances, longer transmission speeds, whereas ultrasonics is basically a sound-based system. So basically, an ultrasonic transmitter would emit a sound of a particular frequency, and based on the time it takes for that echo to return, that's what you're basically using to determine how far or how close a product is to what you're looking at. See, radar transmits an electromagnetic wave, which doesn't require a medium, whereas you're talking about ultrasonic, it needs a medium to be able to transfer to, meaning a medium to bounce back off to come back to it. Where the differences really stand out between the two technologies that help you determine which technology is right for the particular application, you look at the different things. You look at operating pressure. If you have a radar transmitter and you've got a vessel that's completely enclosed, where you worry about pressure waves inside the vessel, then radar will work, but ultrasonic won't, because the pressure waves inside an enclosed vessel are problematic for an ultrasonic type sensor. And you see there, basically, if you got an enclosed vessel with basically a pressure of about 3 bar, which is about 43, 44 psi, then it's a radar application versus an ultrasonic application. And also for people that are dealing in some process stuff, or you're dealing in some hot temperature environments. I'm not talking about hot temperature being out like in the Phoenix sun, but hot temperatures in the application itself. Radar gives you the ability to be able to measure, to do measurements within a high temperature range, whereas ultrasonics, high temperature becomes very problematic for ultrasonic sensors. Also, dusty environments. Ultrasonic works in a dust environment, but it doesn't work in a dusty environment. And what I mean by that is if you've got blowing dust, things of that sort, is problematic with ultrasonics because the sound waves will pick up those dust particles and create havoc with an ultrasonic, whereas you got a radar sensor, you can basically blow right through that, pretty much tune it out. talk about wave angles, accuracies. In general, radar is more accurate than ultrasonic, but there's a caveat with that, which I really don't talk about much, but I'll point it out here now, is we use a lot of ultrasonics for in close applications. So we can get to, inches or even tighter than that resolution with some small ultrasonic sensors. Typically, you can't get to those small ranges with radar. Typically, when you're looking at a statement like this, they're looking at radar that's used to measure tank levels and things of that sort, and they're talking about the accuracies from there versus some of the tighter applications for roll diameter and things of that we do with ultrasonics. And then there's some do's and don'ts, and we talk about the ranges. So, in essence, radar has a wider measurement range than ultrasonics, and I'll show that with some of the discussion later on. Like we've got radar sensors from banner that go out to about 20 meters. Actually, we've got some low frequency banner radar that will go out to 200 meters. Typically, some of the larger radar manufacturers will go out to, almost as much as 300 meters for, we're talking about wave-guided radar, things of that sort. And then ultrasonics, typically, you're not talking to those types of ranges because you're worried about other issues that will affect ultrasonics, the dust, the dirt, the wind, propagation issues, things of that sort. Okay. Let's see. So here I figured I would throw this in to kind of give you an idea of what's the sensing technologies for different levels. And typically when we're talking radar and ultrasonics, probably the most common application for it is some type of level sensing, whether or not it's a process application, it's a factory automation application, things of that sort. So here we talk about ultrasonics, some of the features, some of the limitations, applications. Now this chart here for the ones that are on here, maybe some of their salespeople. This is definitely a go-to chart when somebody's making a decision on whether or not they want to use a radar sensor versus an ultrasonic type sensor. This chart here shows some other sensing technologies. I mentioned capacitive. You can also do some of these technologies using, photoelectric type sensing technology. Every sensing technology has its pros and cons. But what you'll find out there in the world is that when people are doing tank level, for the most part, they've got a ultrasonic sensor attached to it or a radar sensor attached to it, whether or not you're looking at a pharmaceutical application for some of their storage tanks, cosmetic applications for storage tanks, bulk storage facilities in the agriculture industry, roll diameters, things of that sort. You typically look at ultrasonics or radar type technology. So I threw this in as a definite go-to application chart. So if anybody's got any questions on that, let me know.
Todd, I got a question. First of all, those of you on the class, I sent this presentation out to you. It's in your email. But being a neophyte to sensors, could you give me an idea of, there seem to be a lot of advantages to radar versus ultrasonic, but price-wise, can I get a sort of a perspective on the pricing of the two versus each other?
Well, depending on who you're talking about. Toward the end here, I talk about different manufacturers, but it's pricing can vary. If you're looking at some of the, let's say Banner Engineering, some of their radar sensors, anywhere from $299, $399 to $1,000 when you get to some of the larger radar sensors that are used for collision avoidance and things of that sort. I lost a radar application in Bakersfield to a customer that Dan knows, a company called Rain for Rent, and they do storage, portable storage for water, wastewater, and also oil and gas. The engineer there opted to go with a waveguided radar from Emerson with integral wireless technology. That was about a $10,000 waveguided radar system. And we could have done it with a banner system, with a $399 radar plus another, $300 or $400 for, emitter receiver. You're talking about another $1,000 for the emitter receiver pair, and we were $8,000 to the good over Emerson, but they opted to go with Emerson. So there's a lot of caveats with it, Pierce. When I talked about where you use it at versus not, one of the things I didn't have on that slide was radar works can be used in C1, D1, or C1, D2 areas. We don't have a product that operates in those environments. Some other manufacturers do, but when you start operating in classified areas, the price goes way up on a lot of these radar systems. And the guys that really play heavily in either the waveguided radar or even the cone radar systems in that market are the Emersons of the world. SICK plays in that market. Vega plays in that market. You'll find some Snyder stuff in that market. Industry Hauser plays in that market. And those are typically high-end, process-oriented type products. We typically don't run into Emerson, Industry, even some of the SICK stuff in what I'd call traditional factory automation applications. You will run into them in a process application. Does that answer your questions? So that's why it's really the application. You look at the application when you're talking to engineering. It's definitely important to find out exactly what environment you're operating in and what are you trying to do. And then you can take a look at the technology that's going to be best at that application and look at the costing. Banner does ultrasonics, Turk does ultrasonics that are anywhere between, a couple $100 to, maybe $400 or $500 max in some of our ultrasonics. Once again, the big guys in that are doing the larger systems, the Emersons, the Industry Hausers, you're talking $1,000 up to a few $1,000 for an ultrasonic based sensor technology.
Hey, Todd.
Yes.
Do you think some of those customers just have a process state of mind going on? They're used to using Emerson, Endress Hauser, people like that, and they just don't get something that gives them the same performance they need for the application that's not from a process manufacturer, and it's a lot lower cost.
Oh, we totally agree. Now, the other thing too is if you're in the oil and gas market, or even some of the stuff that's in pharmaceutical, a lot of the larger guys that I would say, they have embedded heart in a lot of their systems. Most of these manufacturers don't communicate heart, but they think they need it. So that alone is a sticking point when you're trying to present a product to a competing product in that market. But for the most part, Dan, I would totally agree. It's what they're used to. Like I deal with Era Energy. Era has a bunch of E&H stuff out there and a bunch of pissed off engineers because, why do we have E&H out on this site when everything else that we have out here is Emerson? So you have a lot of that corporate mentality in that this is the only thing we want in our plant. But one of the things that's changed over the years is cost, and everybody's looking to control costs. Everybody's looking to finally start taking a look at stuff that if they don't need a classified product, then they're willing to listen. Whereas in times past, they really didn't care. You know, Emerson is here, E&H is here, Snyder's here, Vega's here. This is the only thing we want. I call on Amgen in Thousand Oaks. I deal with an engineer out there for tank level. They got some Emerson, most of their stuff is Vega. And in my conversations with him, it was all about heart communication. I'm like, do you even use heart? Well, we set up our instruments with heart. And most people, that's all they use heart for, is they have a programmer that goes out and they basically set up their configuration. And then that's it. They're not basically tied in from a heart communication standpoint. They program it in heart, and then everything else is done over Ethernet IP.
Is heart a protocol from Emerson?
No. Heart is, I don't know if Emerson started heart or not, but E&H, Vega, a lot of the process people use heart. Heart is what I would call analog IO link. Basically, it operates in that fashion. It gives you a bunch of process data that if they're truly tied in to the system, they can take a look at a particular device and know exactly what's going on, get all the same type of process data that you get with IO link. It doesn't have the distance limitations that you have with IO link, but it gives you all that process data. And a lot of manufacturers think they need that, but when we really drill down and talk to them, they really only use it when they set up a device. So if they have a device that fails, they can go out and hook their laptop to it and basically analyze the data that's going on in the transmitter, and then make a decision based on that. But they don't have that information basically flowing down to them on a continuous basis. Most customers don't anyway.
Then on an application standpoint, if they need that setup, they still need to have it then, right? Or is that just a superfluous need? They don't really need it to set up the device.
Well, they use it because it's quick and easy setup, because they basically the same thing where you download an IO link file, you can do similar stuff with heart to set up a device. So you can save a configuration and just download it in the device. For those that use it, a lot of customers, when the device goes down, they pull it, put another one in, and figure it out later. Okay. Let's see. So this kind of basically just kind of an overview of the. So I started looking at ultrasonic sensors, sound waves, basically speed of sound, and basically measuring the speed of sound coming back into the receiver. And this is what I talk about when you're drilling down and you're making a decision on what you want to use. Definitely look at environmental conditions. So if you got a customer that's dead set on radar and they really don't need radar, ultrasonics typically is less expensive than radar, and it's used in a pretty wide range of applications. But once again, pay attention to the environment, whether or not pressure, temperature limits, accuracy, what kind of accuracy you need, what kind of performance you need in those particular applications. Looks like I put the same slide in there, Pierce. You're supposed to pick that up for me. Okay, this is from an ultrasonic standpoint. Here are some typical ultrasonic applications. that you would find in some within the process world, but definitely a lot in the factory automation world as well. Solid level measurements, solid liquid level. Probably the one that we probably run into most is this type of application for ultrasonics. Anti-collision detection. Typically, ultrasonics are used a lot in some of the, typically it's been used in some AGV applications. It's used in, I guess, to, just monitoring, equipment around a plant. So detection whether or not people are coming into a hazardous location, hazardous from a collision standpoint. Anti-collision, we'll talk about this later on. I see more radar in anti-collision than I do ultrasonics. People detection, Disney uses ultrasonics where they basically have ultrasonic sensors mounted in the ceilings to detect people in specific areas. It's not a safe application. They just need to know whether or not somebody's in a particular area so that they can trigger a ride or an event in an application. So ultrasonic for people, it's been used for quite some time. A lot better in a lot of applications than using photoelectrics because you don't have to worry about clothing color, reflectivity, things of that sort. It'll basically pick up people in a specific area. If you don't need to drill down from a count standpoint, you just need to know whether or not people are there. Ultrasonics is a great product for those applications. Contouring and profiling. This is a factory automation application, or whether or not you're looking at the contour of a car coming down a production line in an auto plant, or you're looking at a contour of product coming through a roll press application. You just need to know that it's meeting the specific profile, specific flatness. Presence detection we talked about. Sorting, pallet detection with forklifts because of the wide range of ultrasonics, and then bottle counting. If you got bottles that are different colors, opaque and clear, photoelectrics a lot of times will have problems with that. Ultrasonics, as long as there's a solid object out there to look at, whether or not it's clear or not, ultrasonics will work in those applications.
When you talk about bottle counting, what is the reaction time typically on these sensors? On a bottle counting application, you got a lot of bottles flying by per minute.
Well, usually the ultrasonics aren't necessarily used for counting the bottles. It's the fact that, well, I take that back. Banner has some narrow beam ultrasonics, and you're talking, I don't know, probably, I'd have to go back and pull the specs off, and maybe Chad listening on here would know an actual number in terms of the response, but it's a pretty fast response, milliseconds of response on some of the ultrasonics for close detection of objects.
So it's only millis.
Ultrasonics are typically an order of magnitude slower than photoelectrics. That's kind of a good rule of thumb.
And a lot of times on the bottle counting, Pierce, it typically isn't necessarily high-speed application. It's bottle detection that's there. To Chad's point, when you're talking high speed, typically you're looking at a photoelectric from that regard.
Yeah, a lot of the ultrasonics will end up being for like zero pressure accumulation accumulators. So just, is there anything sitting there for longer than X period of time?
Yeah. So since we are Banner, I did put up here's a Banner ultrasonic comparison chart. So you can basically and this answers some of your questions there, Pierce. So you see the ranges of ultrasonics and also some of the resolutions of ultrasonic. Now, take in mind that these ultrasonics, for the most part, are not the ultrasonics that are competing with some of the larger process manufacturers. They don't play in this world, but this is a world that Banner has excelled in for years, in doing some pretty tight sensing range, pretty tight resolution, repeatability type products. Whether or not we're talking, some of their analogs, or so we're talking some of their discrete outputs. And most of the Banner product gives you the ability to give you both types of outputs, either discrete or analogs, but also the Banner ultrasonic, you've got limited ranges as well. Banner only goes up to 8 meters on their ultrasonics. Whereas you're talking some of the bigger guys that are going, 20, 30 meters in some of their ultrasonic sensing bands. So this is what makes Banner so practical for factory automation applications, because the tight sensing ranges, the fast responses, but also the cost points. You're talking a few $100 as you go through the range of these ultrasonics. And then this
makes them cost comparative to the photoelectric sensors.
I'm sorry?
That makes them cost comparative to Banner's photoelectric sensors?
Well, depending on what sensor you're looking at, typically you'll find ultrasonics a little bit more expensive than a lot of their photoelectrics, until you get into some of Banner's laser photoelectrics, like when you get into the Q4Xs and those type of products, where you get into some higher cost points. But some of the more generic photoelectrics that Banner repurposes their housings for, or uses for ultrasonics, the photoelectrics are definitely less expensive.
So therefore, you would go to the photoelectric unless light is not appropriate, and then I imagine ultrasonic has usage in places where light can't effectively be used.
Correct. I started out talking about the different applications or the different environments, things that you need to be concerned about when you're talking ultrasonics and radar. Typically, at least from my standpoint, I don't know if Chad or any other guys operate in this fashion, but when I look at the sensing application, and it used to be before we started doing more in the ultrasonics and radar, I look at what's the best type of technology for the application. I always say, if I can do something, if I'm looking at a metal object and I can be close to it, I don't care who I'm talking to. If I can see it with a prox, I'll look at it with a prox all day long, because it's reliable. Once I can see it once, I can see it every time. And then from there, I started looking at photoelectrics. And then when I look at photoelectrics, I look at through beam, because it's the most reliable. You got a emitter receiver, you break the beam, you've seen the object. And then you start looking at manufacturers, customers that don't necessarily want to power up both sides. They don't have room for that. So what do? They look at, okay, well, I go from a through beam, then I start taking a look at a retroreflective, which you see in a lot of packaging applications, where you've got a sensor that's got an emitter receiver in the sensor itself, and then you got a reflector on the other side, and once again you're breaking a beam. And then you go from retroreflective, you start looking at diffuse, which is basically spitting out a beam and basically reflecting back on the object. Things you need to worry about with those applications is the reflectivity of the product, the range of the product, dust and dirt in the environment, things of that sort. And then you start looking at ultrasonics, Once again, if you really look at the cost points and then you build up from that, then you go from the photoelectric, then you go to ultrasonics because it's a little bit higher price typically. You look at all the different ultrasonics in terms of range, beam angle, response, resolution. You go through that whole cycle, that whole thought cycle, and then you jump into the world of radar. Once again, you look at the environment, you look at the range of radar, you look at the sensing cone angle of radar, whether or not I need a tight beam radar sensor or do I need a wide beam radar sensor. Like we use radar for collision avoidance in some of the ports and things of that sort. We're basically looking at huge cranes. So we can tell, we just want to know when we get within a certain range to shut things down so we're not breaking things with hundreds of millions of dollars worth of product. So you see a lot of radar using that application. Banner uses radar to pick up trains in tunnels as they come through. Radar is used obviously quite a bit in AGV applications because of its range and also its immunity to different types of media, whether or not there's fog, things of that sort. Radar will go right through it. Ultrasonic will not. So you run into problems there. So that's why the environment becomes important. The actual application becomes important. And then you pick out the particular product that really meets the application. If you can do it with a photoelectric or prox, do it by all means. But if you can't, then you need to start looking at other technologies and step up. Now, the thing with, and it's funny because and I think Chad brought this up on our huddle last week as he was talking about, Banner and things of that sort, is most of your competition has a complete portfolio of this type of product. When we're talking about competing with the Bouts of the world, the P&Fs of the world, all those manufacturers typically offer photoelectrics, they offer ultrasonics, and they offer radar. So you have to basically be a full complement type of supplier in those areas. That's what Banner does for you from the photoelectric perspective. That's what Turk does. It's all fill-in product, Pierce, where if I can't do it this way, then I've got this product that allows me to come in and solve the application. No different than what you're doing with VFDs and gearboxes. You pick the specific product that's going to solve the application for the customer. And to your point, they might have been looking at radar and they don't need radar. Ultrasonic will be fine. Or they may have a problem they never realized they had because of the difficulties of implementing ultrasonic, and they should have been looking at radar. I did an application out in the desert, out at Rio Tinto, and we're looking at settling ponds. Well, they had a $5,000 A&H radar system out there. They couldn't get it to work. It should work just the way they mounted it. So I went out there with a $600 radar and Banner radios, and that's what they went with because it was easy to implement, easy to program, and what you also find going on in a lot of these facilities is as they downsized and became leaner and meaner, a lot of those engineers there that knew how to do all this stuff are no longer there, or they're basically so heavily loaded they don't have time to figure stuff out. And that's where we come into play. We've got easy solutions, easy to program. We're not charging them an arm and leg for software like a lot of these manufacturers do, so they don't have to pay for a software support program, and quick and easy to install.
So Todd, just for my reference, if these distance sensors that I see golfers use or hunters use, and they shoot out over hundreds of meters up to almost 2,000 meters in some cases. What type of technology is that?
Typically, a lot of those are using time of flight technology, where they're basically sending out a beam and they're looking at it coming back. And that's what Banner uses in a lot of their and they're typically laser sensors that are being used. And that's what Banner typically uses.
Yeah, there are a lot of infrared lasers.
If you look at cops with their radar guns, they're basically using a Doppler type radar system. Not unsimilar to the Doppler you hear about when they talk about looking at weather patterns coming in. So it sends
Doppler
out
to
a
me
series
is that's a phase shift. So the frequency going out and coming back are slightly different, and they can measure the distance based on the phase shift. Is that what you're referring to as Doppler?
Exactly. They know how fast you're, and then they internally, it's doing the calculation to determine how fast you're going. But the thing about Doppler, if you're not moving, it's not sensing. It's designed to pick up moving objects.
Interesting. Well, okay, that makes sense.
And that's why.
So then the distance sensor for a golfer that is not Doppler.
No, that's a laser technology. And it's a narrow beam. You know, when we talked about when I went through the different photoelectric technologies and things of that sort, one that I left out there was laser, but it basically operates in the same fashion. But the only difference is you've got in a lot of cases, a stronger beam, but also a narrow beam as well. So some of the concerns you might have about interference from objects, you know, to the side, you know, left, right, or overhead, whatever the case might be, you're looking at a focused beam of energy, and then you're looking at that coming back. And because of that, and because of the gain available in a lot of these sensors, it allows you to give you better accuracy when you're looking at you know, slight discrepancies. They're ideal for measurement applications, so you can measure down to the millimeter range. Or in some lasers that we do and other manufacturers do, you know, the submicron range of measurement. When you're looking at some of the stuff like, you know, like a Keyence or an Omron does on some of their ultra high-end laser measurement systems, where they're looking at, you know, microns of resolution. You know, most of our sensors, we don't necessarily want to play in that market because that's not a volume market. And Banner is structured to offer a great product that can be used in a factory automation, typically a volume application where it's price competitive, it's a great product, it's a reliable product, and it's the only one right now that we get paid off of based on that in turn. So makes it even better. Okay. I got a slow machine. My laptop is coming into life. And I did not want to open that up. That's not what I want to see. Well, this is Banner, but there's, and when you're looking at radar, this is what Banner does in radar in terms of the frequencies. A lot of the large radar manufacturers, you know, when you're talking wave-guided radar, typically you're operating at these low frequencies. What does it do is it gives you great detection, especially in bulk items. But then we get into some of the higher frequency stuff that we do with Banner, gives us good detection in a lot of those arenas, also gives us great response speed as well. But what I was trying to get to here, and it didn't come up the way it should have, was the 10 things you should know about radar. This kind of rehashes. Radar works in the extreme temperatures, dust, dirt, low light. If it's dark outside and you're using ultrasonics, you could have a problem. If it's rainy outside or windy outside and you're using ultrasonics or using photoelectrics, you could have a problem.
I'm sorry, I'm confused. Did you say if it's dark out, you can't use ultrasonics?
You can have a problem with ultrasonics in the dark. Because it's all about, I'm sorry, go ahead.
It's counterintuitive to me. Ultrasonic is sound wave frequencies. And you're saying that
frequency, but it's also the wave propagation coming through that as well. Have you
I think what Todd, excuse me, what Todd is meaning is the temperature changes.
oh,
impact.
okay, that makes sense.
Yeah. Have you well, I'm gonna go to that part. And then radar can be used for moving objects. Obviously, you can pick up moving objects as it passes ultrasonics as well, but it'll track it better than radar. Doesn't care about the surface color. Ultrasonics doesn't either, but photoelectrics do in some cases care about the surface color or the finish. That's what I talked about, where it can be mounted in enclosures, so it doesn't worry about pressure gradient like you do with ultrasonic. You'd have to be concerned with that. And then if you've got customers that have the polyester storage tanks, plastic tanks, you can actually mount a radar sensor outside the tank, look through the wall of that material and determine the level inside the tank. Obviously, you can't do that with ultrasonic. You can't do that with photoelectrics. Okay, radar works well both inside and outside, what we just talked about, and then different frequencies for different applications. And that was that little brief thing where I showed you the different radar ranges. The lower the frequency, typically the longer the range. So when you're talking about some of the 24 gigahertz stuff versus the 120, the 24, that Bayer's got a 24 gigahertz sensor that goes out to like 200 meters for collision avoidance. Some of the other manufacturers I mentioned go out longer than that. That 122 gigahertz radar sensor only does 15 meters of range. So typically the higher frequency, the shorter the range. And then beam angle becomes critical, but beam angle becomes critical in a lot of other cases as well. When you're looking at photoelectrics and you're looking at some of the retroreflective stuff, beam angle can be a problem. Beam angle can be a problem with some of the radar stuff, but you really have to pay attention to it when you're looking at ultrasonics and you're looking at radar, because obviously you don't want to pick up devices that are outside what you want to be your focus beam. So if you're looking in a tank and you're trying to determine the depth of a tank, and there's obstructions in the tank that you're looking at, beam angle becomes real important. And this is one of the reasons that this is one of the things that Banner does extremely well, is they give you more focus beam angle stuff for their higher frequency stuff, which is typically shorter distances. And then when you get into some of the longer sensing ranges, you typically end up with a broad beam angle. What a lot of the larger manufacturers will do for their ultrasonics is they basically have a cone that typically extends out of their device, and that basically is controlling their beam angle. Turk does a lot of that with their ultrasonics as well. They'll have sort of a transmitter on their device that basically is controlling the beam angle coming out. Okay. This is just a rehash. I won't go through this. We give you something to look at, but it's just a little bit more detail in terms of radar and the different things that the radar is good at. Chemical, petrochem, I talked about, energy, food, beverage, granular solids, oil and gas. Like I said, oil and gas is most of what oil and gas does is wave-guided radar. And what wave-guided radar is, typically you have the sensing head, and then you basically have a rod that protrudes down into the vessel. And there's different holes along the rod in cases where it'll basically be able to determine what the tank level is based on the waves propagating coming back into that rod. But in those cases, you got limitations because you're basically using a rod to go down in the tank. What they do in a lot of the bin storage applications is, as opposed to waveguide, they'll typically use a cone and basically do a kind of an open wave scenario with radar the same way we would do with ultrasonics. And this is, I think I showed y'all this earlier, but this is what Banner does from a radar standpoint. 120 gigahertz all the way down to 24. And the biggest thing here is you look at the different sensing ranges, but look at the frequencies versus those sensing ranges as well.
Todd, you mentioned those magnetorestrictive technology where, you know, it's a physical rod, and then you get this little magnet ring that moves down the rod and creates a magnetic disturbance, and then you bounce a signal from the source point to the magnetic disturbance, and you can tell where the little ring is, therefore the distance. I remember those to be used quite a lot in injection molding machines and in extruders, and they would basically be in the structure of the cylinder, which to me, if I think about it now, based on what you're talking about, is kind of an expensive arrangement. But yet, what's that company, Balif, used to make a ton of those things. Probably still does.
Balif still does. Turk does as well. PNF. A lot of those factory automation, what I coin as their factory automation type suppliers, offer that type of product. It's a reliable product. But once again, it's an intrusive product because you are putting a rod in the medium itself. So if you've got cases where you worry about a medium that would stick to those types of rods becomes problematic, that's not the type of technology you're using in those applications.
So, is that an application that has reached its limit in terms of time, and we have a better technology to replace it?
No, that technology is, what you know about industry is if it works, and if it ain't broke, don't fix it. So in a lot of those applications, if that's what they're using, they'll continue to use that technology. Can they come in and deal with use some radar in those types of applications? Yeah, but once you get into like Turk, for instance, they do a wave-guided radar for small tank applications, pharmaceutical applications, where the maximum sensing range that you get with their product, which is basically a function of their rod lengths as well, is about 1.5 meters. A lot of the bigger guys do longer ranges, but it's also way more expensive. So once again, you look at the application, you look at the manufacturer. It's okay. What works in this application? You know, if I do a magnetorestrictive and it's going to cost me $2,500, I'm not going to put a $5,000 radar system in there if I don't need to. And I get the repeatability, I get the reliability out of that product. Now, will it go away? I don't see it going away in the near future. I don't know what you see out there, Chad.
For that application, it's kind of the perfect solution. You know, there's no really other better way to do it. You could do magnetic encoder and other things, which, you know, that's just more expense. If you think back to that kind of encoder thing we talked about here a month or so ago, where Turk's got the non-contact linear transducer family, that allows you to do something similar externally at a pretty good price point.
Yeah, and
Question, again, along the lines of linear sensing of, you know, maybe a couple meters on machinery. And right now I'm wrestling with trying to find solutions for what I believe is an aging out technology, and that's the glass scales used on CNC machines. And, you know, we've been trying to find an inductive solution, blah, blah, blah. Is there, just if you were to take a clean sheet on this, you're trying to measure less than a meter on a XY table and a Z axis on a, you know, typical vertical mill. There's a lot of that going on in our territory. Reason I say that is those companies, everybody from Haas at 1,000 machines a month to the little guys that are bringing in Indian and Taiwanese iron and hanging controls on it to get U.S. content. There's probably 20 different OEMs in our territory. And when they need scales, they're going to Heidenhain. Heidenhain bought a company to do basically inexpensive glass scales, but they're problematic. Is there a technology that you would think would work better?
For what we offer, like from a Turk standpoint, you know, what you found out is typically, in their particular case, they have limitations in terms of the output requirements that you need. They can get to probably 70% of the resolution that that a lot of your customers require, but they don't necessarily give you the clean output that you get from some of the Heidenhain product. And that's where the problem ends up being. Any types of these technologies obviously aren't going to work because you aren't getting the resolution and the repeatability that you're getting out of a glass scale. But I don't know of anybody that we have other than what you've looked at from the Turk perspective to fill that void. And I don't know, you know, what some of the other people on this call might have as an offering, but from what we have to offer right now, we don't have anything that really solves that for you.
Yeah, Pierce. So like that QR24 from Turk, that non-contact linear transducer. Best case, the enhanced version, I think, is about 1/4 micron accuracy, and we can get an SSI output, but that's about it.
Exactly.
So no laser or anything like that would be appropriate here?
Well, when you're putting when you're doing laser measurement, it's a question of what you're looking at, and like I just sold a laser product to a customer up in Oxnard, but they only needed a millimeter of accuracy. and they're basically, you know, looking at an object as their machine approaches a cutting point, and then goes from there. So in that particular case, it worked out fine. They used our Q4X. They could use an LM product if they wanted higher accuracy, but they also have on the rest of the machine, the movement of their machine, they got a high scale on the rest of it, on that machine, where they really need that super tight, high resolution, high accuracy feedback into their equipment.
Okay, so laser is not, I mean, laser can be that accurate, or can it be? Can it be accurate to 1/10 of a tenth? Over a meter?
I don't.
Short answer is no.
Yeah, I would say not with what we do.
Fair enough.
Not with what we do. And then the other thing too is laser brings other conditions into play that that aren't in play with these scales. Then you really have to start looking at dust, dirt, anything that might impact that as well is not impacting those scales. So.
Okay, thanks.
Right.
Fair enough.
And then here, and I know we're closing at the end of our time, but here basically I put a list of ultrasonic manufacturers, radar manufacturers. The list is pretty much identical. And what you see on there is that all these suppliers offer both technologies because, in essence, well, they offer for a couple different reasons. One, because the technologies really complement themselves as they go through. I mean, as I talked about how you approach an application and looking at what type of sensing technology works best in those applications. Well, when you're looking at ultrasonics and radar, suppliers go at it the same way, but also if you look at the suppliers, you look at how they compete with each other, they're also well aware that they need to offer a full complement of product, because if they're selling radar for an application for a large customer, they also run into applications at those same customers that can be done with an ultrasonic type sensing technology. So they need a full gamut of products to offer, whether or not you're talking, like the Emersons and industry housers for either waveguided radar or open horn type radar, whether or not you're talking different types of ultrasonic technology. ABB, huge player in the process industry. You don't run into ABB in factory automation for their product. You don't run into industry housing or Emerson so much in factory automation in their product, but you will run into them in the process world. With Banner and Turk, you run into P&F all the time. You run into SICK all the time. You run into GEMS. You run into a lot of these manufacturers that are being sold through Automation Direct online all the time. I didn't list Balluff on here. You'll run into those players all the time, and they all offer a full complement of ultrasonic and radar. So it's about being aware of what you have, and most of these you'll find that Banner and Turk and us on the call, we don't necessarily say them hand in hand, but between the two of them, they have a complement of product that allows you to be competitive and solve 95% of those applications that need to be solved.
So you're saying that we cover 95% of the applications?
95% of the factory automation applications that you run into. When you get into some of the larger bin type stuff that you typically see a lot of the process people play in, we have our limitations. We don't do area classification on any of our products. All the big guys do. We don't do, like Banner doesn't do any process connection much on any of the product. Turk has a limited offering of process connected ultrasonic and radar. Banner doesn't do that at all. All the other big guys, that's their world. They offer that. The big guys offer stuff in stainless. We don't do stainless. Turk does some stuff in stainless. Banner doesn't do stuff in stainless. Most of Banner's ultrasonics and radar are in a plastic, quote, plastic housing, so to speak. So you have your limitations. In a lot of dairy applications where you need a smooth barrel, you run into some difficulties with that with Banner because most of their stuff tends to be a threaded barrel with the exception of one of their ultrasonics. All the other guys, they know that. They play in that world. You've got explosive environments where you need intrinsically safe rated product. The big guys play in that world all the time, so they offer that with their product. Loop power devices, they offer that.
Sensors qualified to do that if we run through an intrinsically safe barrier?
It can, but you have to sell that versus if you're going out to an era, or you're going out to or you're in the C1 D2 area in a biopharmaceutical, they're going to want a device that's embedded intrinsic safe, as opposed to what they got to go through to make it that way. So if you're ahead of the game and you're right there from the get-go from an engineering perspective, you can offer up intrinsic safe product or intrinsic safe barriers, and then like the application you worked on, Pierce, where you
for that LNG test stand, yeah. Okay.
Yeah. So, all right. So I know we're at the end of our time, and hopefully I didn't ramble on too much.
Not at all. Thank you very much, Todd. I learned a lot. I owe an apology to Ian because I didn't mention that the time of this class is California time, and Ian is in Phoenix, so he got up an hour early. My apologies, Ian. We will state clearly henceforth that this is a Pacific time or California time. Other than that, we have a class next week from Sasha Marcroft, who will be talking about, and it's not very clear, unfortunately, I'll make it clear when I redo the schedule, but it says ironless core versus iron core and when to use. That's on the March 11th class with Sasha. And that refers to linear motors. So it's a very narrow topic. But it's a good question between iron core and ironless core in terms of when to use which in a linear application. That'll be next week's class. The class after that will be soft starts and soft starts versus other type of soft starting methods, and also a comparison to when you would go to a VFD versus a soft start. And we'll be talking about soft starts in the low voltage and medium voltage realm. Medium voltage is where the money is. And for those of you out in Arizona, there's a lot of business in the medium voltage soft start arena. So
FYI, next week, it will be 7 a.m. Arizona time after daylight savings happens. So
that's right.
Get it by week.
Pretty much. Okay. Yeah, you guys don't change time, right?
That's right.
Fortunately, I don't know why we do. But anyway, that's another discussion. Okay. Thank you very much. It's 8:06. Time to go to work, and we'll see you next week.
Thanks, everyone.
Thanks, everyone.
Thank you.
Thank you.
Thank you, guys.
Thanks, Pierce. Thanks, Todd.
All right. Thanks, guys.
Have a great week. Chris.
Hey, Pierce.
Hey, how you doing?
Doing well, thank you.
I'm going to share my screen and bring up a and what did I just do? Hang on a second. I think I just messed up.
No problem. Take your time.
Okay, can you see this picture?
Yes, I can. And I saw the video also before. Yep.
So, this one shows a slightly different motor than the one you sent me.
Huh.
My question is this: I could basically eliminate that belt drive between the motor and the gearbox,
Mm-hmm.
turn the motor 90 degrees, in other words, facing down, and connect it to the worm box and eliminate that whole claptrap in terms of the belt drive and accomplish the same thing.
Got it.
Is that of interest, or is there some reason why they want that belt drive there?
That's a great question, Pierce. I don't know.
I
All
spun
I
up a
know-
proposal, a preliminary proposal, doing it both ways.
Okay.
If we do it and preserve the belt drive, there's going to be some cost associated with adapters. Much, but still some, and that'll have to be, excuse me. We'll put that on motion to do.
Mm-hmm.
If I turn that motor 90 degrees and mount it to the right angle gearbox, I eliminate that entire assembly and all of the bracketology.
I get it. Yeah. 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 I wonder why. I mean, in your experience, have you seen reasons or situations where people use the strange belt box assembly for? Could there be a reason for it? You mentioned slippage before, I believe, or something where you want to do something with the conveyor in a certain way, but why would somebody ever use this weird belt setup versus mounting the motor upright direct on the gearbox?
Well, that is the question. Slippage, but in this case, it's a grooved belt. So there's a
Mm-hmm.
lot of surface area on the belt, and I don't think there's going to be much slippage there. And you could accomplish the same thing by putting the torque limit into the VFD. And the VFD, it is a VFD because it's a VFD duty motor.
Yeah.
The other reason that you would want to maintain this primary ratio, in other words, the high speed end of things. So this primary ratio belt is that you can change the belts, the belt pulleys, and change the speed ratio.
Mm-hmm, mm-hmm.
But
Instead of
again,
tuning. Mm-hmm.
but again, that could be a holdback to an old design because they've got a VFD on it.
Got it. Okay, so the VFD, yeah. Okay, yeah, I mean, I don't know the answers to why they're doing this. I have not spoken with the customer directly. This is all communicated and picked up and delivered through Motion. And
Right.
the guy that's on the account, Mario Chicas, is the guy that goes into Crohn's or Pepsi once a week as the standard visit. I don't think he's extremely technical, but we can find out what.
Well, the
Yeah,
guy that would know, is the guy who the man you just mentioned reports to. I spoke to Bryce about this. He came on early in the class this morning, so I just mentioned it to him. And I sent him this picture. So we need to have a conversation. What was that? What's the guy I'm referring to? He came into our meeting way back
Fiore.
when. Yeah, Fiore, that's him. If you could just ask that question, and then I'll send the proposal out both ways. But I'd like to know, because I think we can really simplify things here.
Yeah, I agree. If there's not really a true purpose to this belt, since they use a VFD now, then that whole assembly could look a lot cleaner, nicer, simpler. You don't need that extra box with the belts and the pulleys inside. I mean, yeah, all of that makes sense to me. And I'm happy to ask the question. I think it's great that you have a quote worked out for both ways. And I will gladly ask the question why
Thank
they
you.
would
Okay.
want to use one over the other. Yeah.
Great. Also, just a minor item, but I'm going to send out an updated contact list for the class. And there's some
Yes.
people in the high-tech company that I don't have first names for. If you could just annotate that for me.
Yes, I can.
Okay.
And by the way, thanks for inviting everybody. I'm still confused a little bit sometimes because it appears to me that the email invite has now 100 and I don't know, 150, yeah, something like that. And that looks good. And when I scroll through that list, when you click on that list, you can scroll through them, and I see all, from what I could see when I scrolled through it, it looks like all of the people are now invited. However, when I'm in the Teams meeting where we're in right now, if I go to people up top, and then it shows in this meeting, there's still you, me, and Mason in there. And then it shows others invited. And under others invited, I don't know if you can see, I can share my screen so you see what I'm
Yeah,
talking
no, I
about.
can see that.
Yeah.
I don't know
So
why that's different.
there's 71. And it's not, it doesn't really, I'm just trying to figure out what the heck's going on with this invite and this Teams thing. Maybe we don't see them all on there, but
No,
I'm
the
not.
teams list is not relevant. You can click into my class by just hitting the link that I send on the email.
Got it.
Now, they're not members of the team, and I'm going to update that. The reason I've hesitated doing that is that we still have issues with the team's functionality, and the only reason you'd want to be part of the team is that you could access the file of recorded classes.
Yeah.
And I think we've decided that we're not going to bother with that because Teams cleans it out after 90 days, and we want a permanent record. So we're going to either put it on OneDrive or Dropbox, and that's a permanent record, and people can go there and download the classes that they want.
Got it. Sounds like a good plan. Okay. Well, I'm still hoping that there will be some more from the Arizona group joining over time. I'm sure we'll get some to join, but a couple of them.
It's a process, Chris, and eventually we want to build this thing up to about 30.
Yes.
And we're sort of a third or half the way there now.
Yeah,
But
I
it
know.
just takes time.
It will, and I'll get people enticed when I see them live. I won't send out any more email reminders on this, but when I have live conversations with people, the next round of reminding them will be when I speak with them live, not with another email, and then see if I can get a few more to join. I think that we have now 3 or 4 from Arizona coming in on a regular basis. I hope I can give you a few more, or give us a few more of those guys.
Yeah,
But
perfect. And some of your people are asking for the recorded classes. So it's just taking time for Chad and I to figure out how we want to do that.
Yeah, I could see high tech being interested in the recorded classes too, because they record all their team meetings internally also. So what's the game plan, time, or step? The first step, do you want me to first ask the question why they are using the belt and pulley setup, and if they not would prefer to use a direct mounted gearbox to the motor setup, or do you want to send a quote and we ask the question along with sending the quote? What is your preference on that?
The question, I'll get the quote out to you when I can. I'm waiting for applications engineering to come back to me for something, so I can't. I didn't make this a high priority at Cone.
It's okay.
So, but let's just do it in parallel.
Yeah, I like that approach. Okay, I'll just wait until I see the quote from you, and then I'll take it from there.
Sounds good.
Thank you, Pierce.
Okay, see ya.
See ya. Bye.